ROS2 parameters are very useful when you want to create nodes that you can configure to use, for instance, with different robots. However, if you only implement the basics, you will not be able to change the parameters while the node is running. So in this video, I will show you how to do exactly this using ROS2 and C++. Hello, I'm Roberto from the Construct. So I will be using the online platform from the Construct. Go to theconstructsim.com and you will be able to create an account and follow along with this exercise if you want, or visit one of our courses. So in the video description, there's a link to this project that I will run now. And if you click on that link, you will have a copy of all the files that I will be showing here, and you can practice on your computer. So this video, as I said, is about how to enable live parameters using ROS2 and C++. So basically, let me show you an example. I will launch simulation here, and then run a node. That is a very simple node that does just object avoidance, and we will see it running now here in the simulation window. So the robot moves forward when it detects an obstacle, in this case the wall. It will turn to the left, and then it will move forward again until it detects an obstacle at a specific distance, and turn left again until it doesn't detect an obstacle, and then it will move forward, and so on. So let me show you what's the problem when you implement just the basics of ROS2 parameters. So this node is called obstacle avoidance node, and we have 3 parameters here, like extra parameters: the angular set velocity, linear x velocity, and the safety distance. So let me get what the value of the safety distance node is. So we will use ROS2 param get, the name of the node and the name of the parameter, and I have a value of 1.5. So this is in meters, so when there's an obstacle detected that is closer to 1.5 meters, the robot will start turning. That's basically what this parameter is. But now let me change this parameter, and we will set it to 1 meter, or even closer, 0.5. And we get here the response that the parameters was set successfully. So if I get this parameter now from the node, I will get a value of 0.5. So this is the value. So let's see how the robot behaves. It's moving closer to the wall, and now it's turning. And since each of these squares here in the simulation is 1 meter, we can see that the robot really just didn't change the behavior of the robot. Even if we changed the value of the parameter, the robot is still kind of using this old value of 1.5 meters. So let's see a different parameter. Here we'll get the parameter for the linear x velocity, which has at the moment a value of 0.2. 0.2 meters per second is the linear velocity of the robot. So let me set the linear velocity of the robot to 1 meter per second. Just an example. The parameter was set successfully, but the robot, it's not moving faster now. It's exactly the same velocity that it was before. So why? because parameters do not change automatically the code that is running at the moment. So we did a change in the parameter of the node. We can confirm this because if we do a bit rots2 parameter get, we will get the new value. But the code that is running, it's based on a variable that is set, and this variable was not changed. So this is why we must add a parameter callback function in order to change the value of the variables that will at the end set the velocity or the distance here or whatever you want to change on a parameter on this node while it is running. So let's do that now. I will kill this and the simulation too, because we will have to restart it, and we'll open a code editor window. Maybe I don't need it that big, so this is enough. Great. So this is the source code of this object avoidance node. I will not go into details here. You can open the project and you will find code comments, and if you're interested you can look at it. What I will do now is focus here on the parameters. So we have this node, the constructor here, and we're declaring the parameters and we're getting parameters. Basically these are the default values. So here is a safety distance, a default value of 1.5 meters, and a linear x velocity of 0 to 2 meters per second. Great. So and those values are stored here on this linear x velocity variable, and this d variable, so which is this one here. So let's change this node so that we can have a live update. First we need to add like this, create an instance of the parameter event handler. I will do it like here. After declaring the parameters, we are making a shared pointer to this object here, parameter event handler, right? And then what we need to do is to set a callback method. In this case it's a callback method using a lambda function, and the name is basic callback underscore linear x, like the to have a reference to the parameter that I will change now, the linear x velocity parameter. And in this case it just prints out to the screen what's the update, so the name, the type, and also the value. And then I am assigning to this private member variable, which is here and here, the value p, which is the argument here, parameter. And then I have to add this line here, which is basically this callback function. So I am calling this method add parameter callback, and I must define the parameter, the name of the parameter that it will listen to for any change, and the callback function. So the callback function, callback linear x, which is what I just used here as a name. And well, we have two here, two new member variables, this one and this one here. And so we will add them to our private member variables. So here down there on our private member variables, let's add this, right? This param underscore subscriber, which is this one, and the callback handle, which is this one, which we just added. And that's it. Basically, I save this file and let me just build this package again, and then we will run it and see if there's a difference. Source install setup, and yeah, let me launch it. First the simulation, and now the node. So we see the node is running, and let me get the parameter, the linear x velocity parameter. At the moment it's 0.2, which was the default value. So let me set a different value, just 0.8. And I get parameters successful, and if you notice, the robot is moving faster now. And if you switched here to the other terminal where I executed the obstacle avoidance node, I have this line here, this log line, which was here on the callback, which just prints out that it received this parameter and a value of 0.8, right? So let me just set it slower, 0.1, when the robot is moving forward, and see if it updates. Well, now it's turning. And you can see the robot is moving slower now, because we did a live update of the parameter to a value of 0.1. So that's it. Basically, that's it. Here you can find the few lines of code that you would have to add to your code to create this parameter callback method. On the top of this notebook, there's a link to the original ROS2 documentation where you can find more details about it. And that's it. If you liked this video, please subscribe, share it with your friends, give it a thumbs up, and thank you very much. See you in the next video. Bye.
The ROS2 intermediate course covers how to create launch files for ROS2 using different formats, like for instance Python, XML, or YARN. You will also learn how to work with parameters in ROS2. The course also covers how to manage threading in ROS2 using executors, or how to handle callbacks using the callback groups. You will also learn about a couple of very important concepts in ROS2, such as the quality of service and DDS. Finally, you will also learn how to work with managed nodes in ROS2. Start learning now!